Hold on to your lab goggles. There's now a third, quietly rebellious member in the magnet family, and it refuses to play by the old rules. While textbooks still divide magnets into the classic duo of ferromagnets, your fridge door stickers, and anti-ferromagnets, the silent partners inside hard drive read heads, a fresh study just stamped confirmed on a newcomer called the Altermagnet. But here's where it gets controversial. This magnet doesn't act like a magnet at all, at least not in the way we're used to. A team led by Satoshi Iguchi, associate professor at Tohoku University's Institute for Materials Research, has just unveiled the first optical proof that an organic crystal, yes, the bendy, carbon-rich stuff you'd sooner expect in a solar cell than in a magnetic device, carries altermagnetic DNA. Their report, freshly published in Physical Review Research, reads like a detective story in which light itself is the informant. Why is this a big deal? Traditional magnets announce themselves with a net magnetic moment. Bring two ferromagnetic paperclips close, and they snap together with a satisfying click. Altermagnets, however, keep their magnetic moments perfectly balanced, so that, to the outside world, they appear magnetically silent. Yet, like a poker player with a tell, they still twist the polarization of reflected light in a way that only a magnet can. This paradox has made them maddeningly difficult to spot, until now. The sleight of hand came from a brand new optical playbook. Iguchi's group derived a universal light reflection formula rooted in Maxwell's equations, the same 4 lines of mathematics that govern everything from radio waves to rainbows. Unlike earlier approximations that stumble over crystals with quirky low-symmetry lattices, this formula is agnostic to crystal shape. Think of it as a universal translator that lets any material speak the language of magneto-optics. The cast of collaborators reads like a Japanese physics all-star lineup. Yuka Ikamoto and Taro Moriwaki from the Japan Synchrotron Radiation Research Institute. Hirotake Ito from Kwansei Gakuin University. Shinichiro Iwai from Tohoku University, and Tetsuya Furukawa and Takahiko Sasaki also from Tohoku's Institute for Materials Research. Together, they aimed this new framework at the tongue-twisting organic crystal kappa BEDTTTF CuNCN2Cl. Let's call it kappa BEDT for sanity's sake. Using a refined version of the magneto-optical Kerr effect, MOC, the team bounced polarized laser light off kappa BEDT and watched how the reflected beam's polarization rotated. From that rotation, they extracted the off-diagonal optical conductivity spectrum, a fancy term for a graph that tells you exactly how electrons dance under the influence of magnetism. The spectrum revealed 3 smoking gun signatures. 1. Sharp edge peaks that betray a splitting of the electron's spin-up and spin-down energy bands, classic evidence of internal magnetic order. 2. A real component tied to tiny distortions in the crystal lattice, hinting at piezomagnetic effects, the ability to flip magnetic states with mechanical pressure. 3. An imaginary component linked to rotational currents. Picture electrons swirling like microscopic whirlpools that never quite cancel out. These fingerprints, taken together, certify kappa BED as the first organic compound officially knighted into the Altermagnetic Roundtable. And this is the part most people miss. The implications stretch far beyond academic bragging rights. Because altermagnets don't broadcast a net magnetic field, they could store data without the magnetic noise that plagues today's ferromagnetic memory. Imagine ultralight, flexible smart cards that hold terabytes, yet can be bent, folded, and even laundered without corrupting your vacation photos. Or sensors so sensitive they could detect a single molecule of explosive vapor at an airport checkpoint, all while running on a watch battery. Of course, every silver lining has a cloud. Some physicists argue that labeling altermagnetism as a third type is more marketing than physics. After all, the underlying quantum mechanics still resembles a tweaked antiferromagnet. Others counter that the unique combination of spin-split bands and zero-net moment is fundamentally new. So, where do you stand? Is altermagnetism a genuine new chapter, or just a clever footnote? Drop your hot take in the comments. Let's spark a civil but passionate debate. One thing is certain, The toolkit Iguchi's team forged, an optical method that finally sees the invisible, will now be used to comb through libraries of organic and inorganic crystals. The hunt for the next Altermagnet is officially on, and the prize could be nothing less than a revolution in how we store, sense, and process information. Ready to witness the quiet magnet that refuses to stick to your fridge, yet might stick in your next smartphone? Stay tuned, and don't forget to sign up for the SciTech Daily newsletter so you never miss the next twist in this magnetic saga.